Buongiorno, cari signori e signore. Good morning, dear ladies and gentlemen. This is my real pleasure to give a talk at this conference. I will speak about the Soliton mechanism of the long-range electron transport in donor-acceptor systems mediated by polymers or by nanowires. Before I proceed to the subject of my talk, I want to express my sincere thanks to the organizers of the conference and my personal thanks to Professor Papin and Professor Achila for inviting me here and for giving me a possibility to give a talk online. I deeply regret that I can't be present with you and to give this talk in person, and that is because of terrorist Russia's war in Ukraine. And this is a good occasion for me to express my sincere thanks to you and your countries and your people for your support of Ukraine by all possible means. I dedicated this talk to 50 years of Davidov Soliton. The first paper on molecular solitons, as they are also known, has been published by Davidov and Kislucha in 1973. And in this figure, you can see Davidov near the blackboard in our seminar room explaining about formation of solitons in alpha helices. Last year, it was 110 years since the birth of Davidov, and the Journal of Low Temperature Physics, the journal which is published by Institute of Low Temperature Physics in Kharkov, a millionaire city, the city of famous university, institutes, academical institutes, and museum, which has been severely destroyed by Russians bombing and is still under constant bombing. The city in which children have their lessons not in their classes, but in metro stations underground. And still these editors managed to publish the special issue of this journal dedicated to 110 years since birth of Davidov. Among the papers in this issue, there are many papers dedicated to Davidov's soliton, molecular soliton. And I remind you that Davidov's soliton is a quasi-particle. It can be electron hole or molecular excitation, bound with the self-created deformational potential. And this potential is formed due to electron lattice interaction. It can be compared with the polaron effect. In fact, this is a polaron effect, but the electron lattice interaction in this model is taken into account exactly without using theory of perturbations. Up to now, analytical and numerical studies of such solitons in molecular systems of various complexity in different conditions deal with an isolated molecular system. But in real situations, the electron transport or energy transfer takes place in molecular chains belonging to some complexes, like connected to donor or acceptor, or connected to two electrodes, and other situations. So the subject of my talk is generalization of Davidov solitons in one-dimensional systems to the complexes donor molecular chain, quantum wire, acceptor. Why this is interesting and important? First of all, because there is a very large class of quasi-one-dimensional systems. So these are, first of all, biological macromolecules, and a big class, large class of low-dimensional conducting systems like TMTSF salts shown on this figure. Quasi-one-dimensional Bechgard salts, which undergo superconducting transition at high pressure. Polydiacetylene, the structure which is shown here. Conducting platinum chains, other salts at moderate doping, and other systems. But the subject has received a new boost of interest due to synthesis of new low-dimensional materials with very unusual properties. And due to advances in nano and micro technologies, biomimicry technologies based on complexes which include polymers. These are conjugated donor polymer acceptor compounds, donor salt acceptor compounds, copolymers based on thianopyrazine, supramolecular polymers. And at this conference, I found 2 talks directly connected to the systems, donor polymer acceptor systems. Even in biological systems, in photosynthesis and in the redox processes during respirations, there are so-called charge transport chains, which consist of donor polypeptide acceptor sequence, as shown on this figure. At the initial stage, 2 electron pairs, 4 electrons are formed, and then they are gradually transported from one polymer to another polymer along this chain. And during this transport, each unit of the transport chain is an acceptor for the previous one and a donor for the next one. So we have studied charge transport in 2 types of such systems when the quantum wire is modeled as a simple molecular chain or as a chain which has alpha helical structure. In view of the lack of time, I will tell you about results on modeling with alpha helical molecules, since this is a more rich structure. Schematically, it is shown in this figure. The black dot on the left is donor molecule, the black dot on the right is acceptor molecule, and between them there is this alpha helical polymer. The solid line shows chemical bonding, and along the helix there are 3 chains polypeptides formed by hydrogen bonds, and these chains are shown in dotted lines, dashed lines. I will not tell you much about analytical results and will not show you too many formulas, again because of the lack of time. Better, I will tell you about the results of the numerical simulations and then explanation. So, the Hamiltonian of such a system is obviously a sum of the Hamiltonians of the donor, of helix, and of the acceptor, plus the Hamiltonian of the interaction of the donor with helix, and Hamiltonian of the interaction of helix with an acceptor. Hamiltonian of the helix is the Froehlich Hamiltonian. It includes Hamiltonians of an electron, quasi-particle, phonons, and electron-phonon interaction. Electron Hamiltonian takes into account the on-site electron energy, with psi being a wave function of the electron on the site number I, and resonant transfer or exchange interaction with the constant J, which corresponds to the transfer of the electrons from site number I to site number J, and star means complex conjugated. The Hamiltonian of phonons is sum of the kinetic and potential energy. P is the momentum of the site, M is its mass, capital N is length of our helix, and Wij is the elasticity constant of the bond between I and J atoms. Electron-phonon interaction, we take into account only electron-phonon interaction along the polypeptide chains. I remind you that in the chain there are 3, in the helix there are 3 polypeptide chains, strands, and this corresponds to 3 peptide groups in a unit cell. That's why here we have some difference of view with 3 plus and minus 3. And from this, I is the displacement of the atom I from its equilibrium position due to electron-phonon coupling. What is important in our model is that this is electron wave function, and therefore it satisfies the normalization condition, namely that the probability of electron localization in the whole system, including donor, acceptor, and helix, equals 1. To proceed from the Hamiltonian I have shown you, we derive the system of 10 discrete equations, nonlinear coupled equations, and we study them numerically. For numerical simulations, we fix model parameters close to those encountered in polypeptide macromolecules or in bridge-mediated donor-acceptor systems. They're rather close within some range, not very big. So here are these values. These parameters correspond to the profile of the static soliton when it is located, for instance, in the center of the helix. Here, the three colors correspond to probabilities of electron localization on each of the three strands, blue, red, and yellow. And in the figure on the right, it is the probability of electron presence during the helix backbone is shown. So this is summarized by all three polypeptide chains. So we see that this is reasonably localized quasi-particle. I don't show here the deformation, but it is also localized as well. We consider three classes of coupling. The first one is when the donor molecule is coupled to all three strands. The same about acceptor molecule. Another case is, and this is the most interesting case of coupling, the most efficient. The single strand coupling is when donor and acceptor are coupled only to one strand if they are located close to only one strand. And finally, end-to-end coupling when donor couples to the first side and acceptor couples to the last side of the helix. We start numerical simulations with the initial condition when electron is localized on the donor and its probability inside the helix and on the acceptor is equal to 0. 25 dimensionless time units, we see that the probability of electron localization on the donor decreased to 37%, and certain probability of electron is spread over the nearest sites in the helix. And we see that this is rather well described by the decreasing exponent. 25 units of time later, at t equal 50, the probability of electron on the localization on the donor molecule decreased to 25. And we see already here that there is a well-defined, localized bell-type probability of the electron, which moved from the terminal end to position number 50. And there is no probability, zero probability at the acceptor. At time 200, the soliton has approached the opposite terminal in the system, and there is already 35% of electron probability on the acceptor, almost zero probability on the donor, and certain probability inside the helix. And finally, at the final stage, more than 95% of electron is localized on the acceptor molecule, so that our electron has tunneled from helix to the acceptor. And this process occurred with probability equal 1. But the soliton properties and scenario of soliton dynamics depend not only on the parameters of the system, as we know, of the helix, for instance, but in this case also on the parameters of the donor and acceptor, but also on the type of the donor helix and helix acceptor couplings. This figure shows the dependence of the maximum probability of electron presence on the acceptor, dependence on the constant of electron-phonon coupling between helix and acceptor, and different curves correspond to different on-site energies of electron on the acceptor. For the case of the full homogeneous coupling. The second figure shows the same results, but for the end-to-end coupling. And we see that these processes are very, very different. This is much more efficient. And this simulation has been done for time equal 100. Now, if you look at the evolution of the initial impulse, we see that on the first stage, the transfer of the electron to the first side of the helix took place. Then the probability of the electron localization spread within the helix with the formation of the envelope in the form of the decreasing exponent. And then this decreasing exponent evolves into the soliton and some linear sound waves. And this processes the formation of the decreasing exponent as initial excitation and the evolution of the decreasing exponent into soliton and tails are well described by the inverse scattering technique. What is important is also that even at zero initial momentum, the soliton being formed starts moving to the opposite end of the helix, and this takes place because of the symmetry breaking. At the final stage, the transfer of the electron to the acceptor takes place. I underline again under the proper parameters of our system. A very important question about solitons is their thermal stability. I don't have time to go into the details of this problem, but in our simulations, we have considered the worst case for the soliton life, when we take into account temperature only by means of adding the Langevin term to the equations for the atom displacements. And we ignore effect of temperature on the parameters of the electron subsystem. So this Langevin term is written here with function f being the thermal noise, and we choose this traditionally as the Gaussian white noise of zero mean value and of this variance, where gamma is absorption coefficient or friction coefficient, and T is temperature, K is Boltzmann constant. For each temperature, we have performed 100 simulations and computed the mean value of the maximum probability of electron localization on the acceptor for T equal 100 or less than 100 obtained from this simulation. In the dimensionless units which we use here, physiological temperature corresponds to 5.5. And this figure shows the variation of the maximum probability of electron presence on the acceptor at T equal 100 only as function of temperature for different chain lengths. Here, different colors correspond to different chain lengths, and temperature is shown here. 5.5 is physiological temperature. And the same characteristic, but as function of the friction coefficient for different temperatures again, for different temperatures. So we see that this process again depends on the parameters of the system, on temperature, on the length, but for the reasonable for long enough chains at not too high temperatures, the soliton is rather stable, and essential part of its probability is transported to the acceptor. So to conclude, the conclusion is that charge transport on macroscopic distances in donor polymer acceptor systems can occur via soliton mechanism. This process is sensitive to the parameter values, depends on type of coupling, and is stable in a broad range of the parameter values. The efficiency of the charge transport can reach 80–90% for long polymers, 70 unit cells, 200 peptide groups, and is stable at not too high temperatures. Some of these results have been published in these two publications. So I want also to thank my collaborators, Alexander Yeremko, Jinxie Luo, Bernard Piet, and Wojtek Zakrzewski from Durham University. Thank you all. Stand with Ukraine. Grazie.